8 crew members can live comfortably on board the International Space Station. The astronauts' private quarters are equipped with computers, VCRs and telecommunications to Earth. Each astronaut can live here from 3 to 6 months at a time. The habitation module has bathroom and shower facilities, health maintenance centre and a fully equipped galley with all the conveniences of home. Except here, there is no gravity. Scientists in the laboratory module can perform experiments not possible on Earth. The microgravity of space allows astronauts to grow perfect crystals and produce chemicals with an unprecedented level of purity. They experiment with robotics, electronics, ceramics, plants and human cells. Research aimed at advanced technology for new products. An important mission aboard the space station is Earth observation. The luminous blue horizon is our atmosphere. It seems so fragile, yet it shields all living things. From orbit 250 miles above the Earth, the home planet is perceived as a delicate living organism that needs to be protected through international cooperation. The International Space Station's external payloads are attached to a truss structure 500 feet long. Instruments are trained in space as well as Earth. Information gathered enhances research in astronomy, oceanography, geology and meteorology, changing the way we understand our world and our solar system. Space shuttles are a welcome sight. They bring the personnel and equipment that keeps the station running. The space station itself begins in the cargo bay. 28 missions carried pressurized modules from the United States and their international partners. The shuttle brings truss structures, solar arrays and experiments, all to be assembled in space. In the late 1990s, once the station was operational, a new era began. Now that we can live and work in space, it's easy to imagine life on the Moon, or maybe even Mars. Nestled in the remote valleys of California's Mojave Desert is a complex of deep space communications antennas. Without these graceful giants, NASA would not be able to command and receive information from satellites or investigate distant stars and galaxies. The complex called Goldstone has been NASA's switchboard to the universe for many decades. In actual fact, it's one of 3 stations located at equal distances around the globe and linked together to provide continuous contact with spacecraft. The largest of all dishes, measuring 70 meters across, has been in service for over 35 years. Its large ear helped scientists collect data from missions like Magellan, which mapped the surface of Venus. Faint signals from Magellan travelled millions of miles through space and were received by the antenna. Signals that are still amplified, processed and transferred to the Spaceflight Operations Facility at NASA's Jet Propulsion Laboratory. This is the clearinghouse for all incoming and outgoing information. Ultimately, millions of picture elements are assembled from spacecraft data and transformed into unprecedented views of the Venusian surface. Not all of Goldstone's dishes have pointed at spacecraft. As early as 1962, the 26-metre site used radar signals to detect surface features on the planet Venus. A high-tech antenna was added to test new hardware, including equipment that will someday help search for life elsewhere in space. Goldstone is one of America's oldest and most valuable resources. Tracking first began in 1958 with Pioneer 3 and 4, which measured a second radiation belt around the Earth and helped chart a course to the Moon. Antennas tracked the Ranger lunar probes, and by 1966, Surveyor spacecraft beamed back pictures of the surface. Goldstone brought us live TV of the first moonwalk. Tracking continued as early Mariner spacecraft visited some of our closest planetary neighbours. In 1977, a pair of Voyagers began a mission that would send back images of worlds we'd never seen before. Planets with complex ring systems and their tortured, icy moons. Goldstone still receives faint signals from the Voyagers as they head towards the unknown regions of interstellar space. It's a perspective that's thrilled astronauts since the beginning of manned spaceflight. And for the last few decades, crews have looked back in wonder from this unique vantage point, while generating a variety of Earth imagery. Produced with motion picture and still cameras, as well as the shuttle's onboard video system, these images provide a visual record of how our planet is changing over time. And along with satellite data, it offers scientists in a number of disciplines a significant research tool. Oceanographers can look at currents from the right position with respect to sun angles. Detailed cloud patterns are captured for meteorologists, and geologists can see large areas with very high photographic resolution. This, for example, is a satellite image of San Francisco showing its fault lines. Astronauts begin training in Earth observations when they enter the space program, so that by the time they fly, they're thoroughly familiar with the science of photographic techniques involved in the effort. This enables them to make real-time decisions about all the things they're seeing from orbit, including capturing unusual phenomenon not on the original flight plan. Earth observations from the shuttle reveal dramatic changes on the face of our planet. This is a view of Lake Chad in Mauritania, seen by a Gemini spacecraft back in 1966. Shuttle crews flying over Africa in 1985 saw Lake Chad looking like this. The only remaining water is the whitish patch at the upper end of the dark zone, a result of the drought conditions. The fragility of our atmosphere has struck all Earth-observing astronauts. Some have likened it to an egg, not the outer shell, but the thinner membrane within. That is, they say, the tiny membrane of air and gases that keeps us healthy. A major environmental concern is the large-scale burning and subsequent deforestation going on around the world. A number of shuttle crews have documented this activity. The important thing is to recognise that unlike countries, there are no set boundaries to our environment, and that everyone's affected by one another's actions. The year is 1962. Miniature components for the Mercury capsule are examples of some of the developments with potential for other uses in industry and at home. This is a Mercury capsule retro-fire relay. It contains 50 components in a case about 3/4 of an inch by 1 inch by 1.5 inches. Preparations continue in the last half of 1962 for the first two-man Gemini flight, which will ultimately occur in March 1965. NASA develops more space technology in preparation for Gemini. A Gemini spacesuit can be worn for as long as 14 days. It is being tested for comfort and mobility. The boots, gloves and helmet are attached to the suit to provide decompression protection during critical times of flight. The Apollo suit is so far the most difficult to develop. Scientists test dehydrated freeze-dried foods and concentrated bite-sized snacks packaged in edible coatings for space travel use. Water reconstitutes dehydrated food to its original texture. Freeze-dried foods include fruits, meats and fish, which can be stored indefinitely without spoiling. Scientists study how well microorganisms live in a space environment. These studies are important before artificial environments for space crews on extended missions are created. When the first European mission to the Moon, Smart 1, lifted off, a key part of the payload was a British instrument built to reveal the mysteries of the Earth's lunar companion. At the Rutherford Appleton Laboratory in Didcot near Oxford, the British scientists involved in the European Space Agency mission explained why, after so many lunar missions, the Moon remains a relatively unknown and unexplored world. It represents an unspoiled record of the chemical makeup of our own Earth and the rest of the solar system. It offers a view of the past because in parts of its crust or the surface, it holds a record of what was going on in the early solar system about 4 billion years ago. That record has been wiped out on Earth, so looking at the Moon is like looking into the Earth's past. In the heart of the Smart 1 probe is a design and engineering feat by British scientists who have built the smallest and lightest instrument of its kind. The British-made X-ray spectrometer, a kind of chemical identifier, is 4 times lighter than similar instruments built for space exploration, taking less fuel to blast it into space and saving millions of dollars. The spectrometer, or DCIXS, picks up solar X-rays reflected from the lunar surface. As different chemical elements and compounds reflect or fluoresce individual X-ray signals, the probe can read and record the chemical makeup of the Moon. It works because when the sun shines on the Moon, the elements in the Moon fluoresce. This fluorescence is then radiated back to the spacecraft and DCIXS picks it up. It can measure the different X-rays which are coming back. Armed with a complete X-ray chemical map of the Moon, British scientists hope to compare lunar chemistry with Earth rocks to solve a mystery that's baffled astronomers. Despite manned missions and detailed observations, no one knows exactly where our lunar companion came from. The origin of the Moon is actually still quite a mystery. There are some good ideas of how it formed. The leading theory at the moment is that a large body about half the size of the planet Mars smashed into Earth as it was forming, threw off lots of material, and then formed the Moon. But there are still problems with that theory. One of the things scientists hope to achieve with the Smart 1 mission is to try and answer that question and fill in the gaps of our knowledge. Using a pioneering solar-powered propulsion system, the Smart 1 probe will take 6 months to map the entire lunar surface. It could take off from an airport runway, achieve speeds of over 17,000 miles per hour, and fly directly into low Earth orbit. Called the National Aerospace Plane, or X-30, this sleek research craft will hopefully lead to a new generation of vehicles providing affordable, flexible access to space in the 21st century. So that this concept could move closer to reality, a group of technicians, engineering students and faculty members at the Mississippi State University have built a 1/3 scale mock-up of this dream plane. The model was built like a real aircraft, which gave the team an opportunity to apply their theory to a practical project. The model had to be strong enough to withstand the rigors of being transported around by road in all weathers. The goal was to create something that would help communicate what the X-30 is all about, a model that people could see and touch at air shows and museums. At a ceremony in the school hangar with some 500 supporters on hand, the 50-foot, 2,500 kilo mock-up was presented to the public for the first time. In this way, the public can be involved in the future direction of the aviation industry. The difference between space labs and earthbound laboratories is microgravity. Microgravity is the result of being in a free-fall orbit around the Earth. Free fall makes things appear to float when they're actually falling. In space, microgravity can affect the cardiovascular system, the heart, arteries and veins. We know the cardiovascular system becomes weaker in microgravity. It's called deconditioning, and it can reduce the astronaut's exercise capacity during flight. In a replica of the Space Lab on Earth, scientists devised a specific set of instructions for the astronaut to follow in flight. In order to gather the necessary data, the experiment had to be performed firstly on the ground during the flight and after landing back on Earth. The instructions ensured the experiment was carried out the same way each time, enabling the scientists to make accurate comparisons. Another vital piece of equipment on board the spacecraft is the General Purpose Workstation. It provides a shield between the astronauts and potentially harmful substances like fumes and toxic materials. It also provides a container for items that would simply float away if the GPWS weren't there, like water. For safety reasons, any liquid that's spilled must be soaked up immediately. That's because on orbit, liquid doesn't fall to the floor. In space, it could float around and short-circuit a piece of electrical equipment. So thoroughly cleaning the General Purpose Workstation is a safety must. The Saturn V rocket welcomes ASCANs, or astronaut candidates, to the Johnson Space Center. They all look pretty calm, but ejection seat training is just around the corner. You've got to be able to land properly in a parachute. Then, if it's carried by the wind, you've got to have the presence of mind to release the harness. This is the way to gather the chute once you've hit the ground. Now, you may have a head for heights, but what about ditching in the cold waters of the Atlantic? If you land in foreign terrain, you need to know how to construct a trap for food. The parachute comes in handy as a shelter. The compass shows direction, whilst a signal fire shows where you are. And the donning of a spacesuit for the first time is always a thrill. This looks like fun, but in a real situation, it could save your life. The Crew Compartment Trainer, or CCT, gives the ASCANs a taste of what may lay ahead for the successful ones. In the Manipulator Development Facility, the ASCANs get to operate the robotic arm, an integral part of space missions. In the Weightless Environment Test Facility, the candidates suit up for underwater weightlessness training. The SMS, the Shuttle Motion Based Simulator, projects animation showing the shuttle commander's point of view. NASA's T-38 training aircrafts line up at Ellington Field, Texas. It's time for some roll maneuvers, and this is the real thing. The KC-135 flies parabolic arcs to simulate microgravity, the state astronauts are in for the duration of their mission. It's enjoyable for a short time, but after a few seconds, the fun comes to an abrupt end. Training for instrumentation checks is all important for the candidates. Finally, the time of reckoning arrives. The successful ASCANs receive their pins and diplomas, signifying that they have achieved what many of us can only dream about, graduating as astronauts to go where few have gone and to explore the disappearing frontier. "250 miles above the Earth, the home planet is perceived as a delicate living organism that needs to be protected through international cooperation. The International Space Station's external payloads are attached to a truss structure 500 feet long. Instruments are trained in space as well as Earth. Information gathered in eight crew members, robotics, electronics, ceramics, plants and human cells. Research aimed at advanced technology for new product. An important mission aboard the space station is Earth observation. The luminous blue horizon is our atmosphere. It seems so fragile, yet it shields all living things. From orbit can live comfortably on board the International Space Station. The astronauts' private quarters are equipped with computers, VCRs and telecommunications to Earth. Each astronaut can live here from 3 to 6 months at a time. The habitation module has bathroom and shower facilities, health maintenance centre, and a fully equipped galley with all the conveniences of home. Except here, there is no gravity. Scientists in the laboratory module can perform experiments not possible on Earth. The microgravity of space allows astronauts to grow perfect crystals and produce chemicals with an unprecedented level of purity. They experiment with